All right, so today we are continuing down the road of proving triangles congruent. This one, today I'm going to try to make the video a little bit shorter. Yesterday's just got out of hand, and I apologize for that. So this one's going to be a quicker video, hopefully. So getting into this, our goal today is to be able to say I can use the SSS postulate to test for triangle congruence, and I can use the SAS postulate to test for triangle congruence. We're going to get into what both of those are in a hot minute. So, new vocabulary right off the bat. So, an included angle is the angle made by two lines with a common vertex. So, we'll get into that a little bit more, but let's see here. So that's side. Where is side angle side? So side angle side is the SAS one. And so essentially this is where you'll see the included angle. So what SAS says is if you have two sides that are congruent, and then, or if you have two sets of sides that are congruent and corresponding, and the angle, the included angle is also congruent, then the triangles are congruent by that standard. So essentially, like these triangles here, we have ED is congruent to AB, and then EF is congruent to BC, and then this included angle here is also congruent. So therefore, the triangles themselves are congruent. We'll get into that more in a little bit, but I just wanted to give you some context for what an included angle is. So moving on, the first postulate we're going to deal with is SSS, or side. So I hinted at this in the 40-minute video yesterday. If three sides of one triangle are congruent to the three sides of the second triangle, then the triangles are congruent. So essentially the way they write this is if side whatever, if the first side's congruent, I'm really struggling with words. So essentially if all three sides are congruent to the three corresponding sides on the other triangle, then the triangles themselves are congruent. If all the sides are the same, so ED is the same as AB, AC is the same as FD, and BC is the same as EF, then in fact ABC is congruent to DEF. If all three sides match up, then they are the same. So we're looking at a different kind of proof today. You will not be asked to write these. Flow proofs have very little use, in my opinion. Even less than two-column proofs. Two-column proofs are at least a logical form of showing understanding. Flow proofs can get messy and out of hand very quickly, but we want you to be exposed to them in case there is one on like a standardized test at some point. I don't anticipate there being any, but you never know. So a flow proof, the way this kind of lines up is it's like a flow chart. So you have all these different things leading you to your final proof statement. And so in this one, if we go back, they give us that QU and AD are they are congruent, and then QD and AU are congruent, and they want us to prove that triangle QUD is congruent to triangle ADU. And so if we look at this proof, our two given statements are on the right, working towards proving that the triangles are congruent. And then, so the only thing that wasn't given is this DU is congruent to DU, which this is one, again, I alluded to it in the video yesterday. When these two sides are shared, then they're of course going to be congruent because they're the same line. So anytime we see something like this, it's always reflexive property because line DU is going to be congruent to line DU. They're the same thing. It's a wild concept, I know, that the exact same line would be congruent to itself. But that's essentially all we needed to do here, is to say du is congruent to du, and that's our reflexive property by definition. So our proof statement is justified by side, 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 because we were given that two of these, this side and this side, were congruent. We were given that right away. So there are angles, or there are arrows going to that final proof statement. Our final proof statement is highlighted down here in blue. So the two green were given right away. We know those, and then the only thing we needed to figure out was that du is in fact congruent to du, and we justified that with the reflexive property. That's kind of the outline of how flow proofs work. They're not bad for triangles, since you are always just proving that three pieces are congruent, whether that be three sides or inside angle side, where you're proving two sides and one angle. So you only ever have three arrows going into them. But in some cases, flow proofs just get unwieldy, and we don't use them for that reason. That's why I prefer two-column proofs when we do, in fact, have to write proofs. So moving on, we're looking at another flow proof here. Let's go back for a second. So I've kind of spent a minute here ragging on these flow proofs. I don't like them. They're messy. I've kind of gotten that point across, but where I do think they're valuable is they are a valuable way for us to show our thinking. And so that's why we see these a lot with triangles, and that's why there are so many of these in our notes, because it kind of shows us a way that we can think through these problems. So once again, on this next one, we see a flow proof as well. And so I spend all this time ragging on them, but yet we're going to continue to use them in this lesson. So in this flow proof, what they give us is that AC is congruent to AB. So this line and this line are congruent, and then they also give us that D is the midpoint of BC. So if D is the midpoint of BC, then we know that DC and DB are congruent. They're the same length, and that is by definition of a midpoint. So def of midpoint. So that would be our reasoning for that. So now what the question is actually asking us is, okay, fill in this blank. What is our reflexive property here? Which, as we've stated previously, our reflexive property is wherever we have this shared line. So our reflexive property would actually be AD is congruent to AD, would be the answer to this problem. But I do actually like in this flow proof how it kind of shows, okay, we were given AC is congruent to AB. Delightful. Okay, we're given that. We're good to go. Then we have our reflexive property that shows AD is the same in both triangles. Delightful. That's two sides. Now we need to figure out our third side, the CD-DB side. So I like how we can kind of show our we can show the route that we used to figure out that DC is congruent to DB. And we used that they gave us that D was the midpoint here. And by definition of a midpoint, then those two segments are the same distance, so they are congruent. So it's kind of it's a different way to show how we figured out those side lengths being the same. But that's about as far as flow proofs get us, really. I mean, anything other than triangles, they just get unwieldy. But I do think it's a good thing to look at for a way to think through these problems. So continuing on, we are determining whether triangle ABC is congruent to triangle DEF. Now, what I want to do here is I want to teach you guys a new trick. Now, I said this video wasn't going to be as long as the previous one, so I'm going to go through this very quickly, and we will spend some time in class on it. But if this seems like a route that you guys would like to go, then please let me know. I'm willing to spend more time with you so you can understand it better. So typically, what we would have to do is calculate the side lengths of all three sides using distance formula and seeing if the sides match up to prove that these are congruent or not. So what I'm going to do, first things first, what I want to do is I want to label the corresponding sides based on this congruence statement. So side DE, I'm going to call 1, and that's the same as AB. And then BC, I'm going to call 2, which would be the same as EF. And then my third side is going to be AC and DF. So this trick is called Pythagorean theorem, which we do learn later in the year, but I feel like it is an invaluable tool to use right now instead of using distance formula, because distance formula is long and it's unwieldy. So anyway, what Pythagorean theorem says, which like I said, we'll spend more time on this later. What Pythagorean theorem says, I'm going to write this in blue. It says a squared plus b squared equals c squared. So Pythagorean theorem is a method of finding missing side lengths in right triangles. And why this is so valuable on the coordinate plane instead of using distance formula is we can make right triangles out of any of these side lengths that are kind of cut across. So what I mean by that is if we look at, I'm going to switch to red now. If we look at AB, we have a right triangle right here. So if I just draw this in, going straight up and straight left, that's a right angle. So we do have a right triangle here, and we can count these distances. So we have this side length is 2, and this side length is 5. So that is a quick way that we can calculate our side lengths. So just because we do need to spend a little bit more time on this to actually get it down. So let's use this first triangle that I just drew. Let's use that as our example. So I'm going to color this in red to show that this is our triangle we're working with. So I'm going to rewrite this down here at the bottom. Or actually, I'm going to write it over here. So we have a side length of 5, and then a side length of 2, and then we connect it. So we have 5, 2, unknown. So the way Pythagorean theorem works, A and B are always our two smaller sides here. So I'm going to call this A, I'm going to call this B. So my 5 is A, my 2 is B. C is always our longest side, which is called the hypotenuse. So on a right triangle, that's always the side across diagonally from the 90-degree angle. So our hypotenuse is always going to be diagonal from that 90-degree angle. So, and in this case, it's always going to be what we're solving for. Now, the reason I like Pythagorean theorem so much, and this is actually when we're doing distance formula, when we're doing it on the board, this is how I would solve it in my head quickly, by using Pythagorean theorem, because it's quicker. So, anyway, using these values and plugging them into the formula, we have A is 5, so 5 squared plus 2 squared is going to equal C squared. So what we need to do is square both of these, so 25 plus 4 is going to equal C squared, so 29 equals C squared. And then we would take the square root of both sides, and it's going to be a messy decimal, which is fine. Because the reality of this is we actually don't need to write it as a decimal, and we'll get into that a little bit further. I guess it would be 0.9 equals C. So I'm trying to debate how much time I actually want to spend on this, because it will save you guys a lot of time if you learn it this way. So my C length is going to be 5.39. So 5.39 for that one. For this right here, 5.39. Now, we need to see if that side is the same on ED as well. So what I'm going to do is I'm going to draw in my triangle again down here. So we have 2 down, 5 to the right. So 2, 5. Now if we do Pythagorean's theorem again, we are going to do, I'm going to call the 5a and I'm going to call the 2b. So we say a squared, so 5 squared plus 2 squared is going to equal c squared. Now we work this out again, we get 25 plus 4 equals c squared, and we get 29 equals c squared. Then we take the square root of both sides, and we're left with 5.39 equals c. Okay, those are the same. Perfect. That side checks out. Now, some of you may have caught on to this. Why did we work that out a second time? This right triangle that we drew in has the same dimensions. So of course that third side is the same. And that would be a great point to bring up. So if our dimensions on these right triangles are the same, then our triangles are congruent. So as we can see with this one, a 2x5 triangle is going to, a 2x5 right triangle is going to have the same side length for that hypotenuse each time. So I'm hoping this kind of makes sense to you guys and we're not just wasting time here for a little caveat that might make life easier for some of you. But essentially, when we draw in our right triangle, if the side lengths are the same, then they're the same length. So if I'm going to draw in a right triangle for side AC, I'm going to drop it down, and I'm not going to use the colored pencil tool. I want to use the marker tool. So I draw this down, and we have a right triangle that is 4 by 1. So for side FD, I should also have a triangle that's 4 by 1. So I have 1 by 4. So that has the same dimensions. It's going to be 1 squared plus 4 squared for both of them. So that side length is going to be the same. I don't know what it is off the top of my head, but I know that side length is going to be the same because it's going to be 4 squared plus 1 squared is going to equal c squared. And I can do the same thing for this final side. I can go from C to B, making a right triangle, and I can see that the dimensions are 2 by 4 to make that right triangle. And then from E to F, I go up 2 and right 4 to make my right triangle. And the dimensions of that are also 2 by 4, which means that third side is going to be the same for a right triangle. So 2 by 4 is still going to be the same as 2 by 4. So using Pythagorean theorem, I can determine, yes, these are congruent. Like I said, we're going to take some time in class to talk about this. I'm not going to take any more time on the video, but it makes life so much easier when you're finding distance in a coordinate plane. Continuing on. So side angle side. What side angle side says is if you have these two sides that are the same, so one hash mark matches up with one hash mark, 2 hash marks match up with 2 hash marks. So this blue side is the same as this blue side. This red side, same as this red side. And then our green angle in the middle is the same as the green angle in the middle. So if we have two sides that are the same and the included angle, that green angle, is the same, then the triangles are congruent. So that's what side angle side says. So if in a row you have a side, then an angle, then another side that are congruent across both triangles, so the corresponding parts are congruent in each case, then you have a congruent triangle. That's what side angle side theorem says. So in their words, they say if two sides and the included angle of one triangle are congruent to the two sides and the included angle of a second triangle, then the triangles are congruent. All right. I would draw these pictures in your notes. I think they're helpful. So what this says, the wings of one type of moth form two triangles. Write a two-column proof to prove that triangle FEG is congruent to HIG if EI is congruent to FH and G is the midpoint of both EI and FH. Okay, so how we're going to go about this, we're going to go to this next page, and I left the answers in there, which is beautiful. So essentially how we would go about this if I didn't leave the answers in here on accident, we would write out our given just like they stated. Then what we would do next is we would say, okay, FG is the same as HG. And that's based on midpoint theorem. And at the same point, we could also say EG is congruent to GI. Same deal based on midpoint theorem. And then we could also say that this angle here is the same as this angle here due to vertical angles. So in these intersecting lines, they're straight diagonal from each other, or straight across from each other, which makes them vertical angles, which makes them congruent. So now that we have all of that, we can see that we have two sides, two corresponding sides on each triangle that are congruent, and the included angle is also congruent. So we could then say, by side angle side, these two triangles are congruent. And so if we look at this proof, that's essentially what they did. So they said those two lines are congruent based on midpoint theorem in both cases. And then they used vertical angles theorem to say that those two angles were the same as we did here. And then they said the two triangles are congruent based on side angle side. All right. So now a proof where I didn't leave the answers in. Good job, Mr. Wright. So proud of you. So what they tell us, the two-column proof is shown to prove that triangle ABG is congruent to triangle CGB if, so first of all, our proof statement, they just highlighted it here. So we put it down here because that's going to be our last step whenever they give us a proof statement. Next, they say if ABG is congruent to CBG, so that's given, and AB is congruent to CG, that's given. So let's take a minute, let's label those in the picture because the pictures are invaluable to help demonstrate what is being shown. So CGB, so this angle and this angle are the same. I'm not so sure I love this picture, but whatever. And AB is congruent to CG AB. So this line and this line. Okay. Did I label that right? ABG. No, I didn't. I labeled that wrong. Okay. Erase that. So it should have been this angle. I apologize. Reading's been a challenge today for me. Just in general throughout my life, I guess. But whatever. That's why I teach math. So anyway, so now we've labeled all of our given information. Now, in this example, they have our second step written down, which is BG is congruent to BG. So that is these lines. So those lines are congruent, and as I've said before, anytime we have that shared line and we're saying that something is congruent to itself, we use the reflexive property. So a good way to remember that reflexive property, reflect. If you're looking in the mirror, you're seeing yourself, so it's the same thing on both sides. So it's the reflexive property. So then our last statement, our proof statement, we need to use either side angle side or side side side. Well, we have two side lengths that are congruent in each triangle. We don't have three, we only have the two. But our included angle here, so between side 1 and side 2, I'm saying side 1 and side 2 as the number of hash marks they have. So side 1 being these sides with 1 hash mark, and then side 2 being the shared side with 2 hash marks. Those are congruent on both triangles, and the included angle is also congruent on both triangles. So we can say side angle side means that those are congruent triangles. All right? Continuing on. So they want us to use side angle side or side 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 to prove in proofs. Okay, cool. So that those directions make no sense to any rational human. So continuing on, let's look at this. So we have RQ is parallel to ST. Okay, here it comes. We're back to chapter 3. So these two lines are parallel, and RQ is congruent to ST as well. Okay, so they already labeled all of that for us, which is delightful. I'm going to highlight this in red just because they used red marks to show it. And then our proof statement is that QS is congruent to, or angle Q is congruent to angle S. So this is going to be slightly longer than the last proofs, I believe. So we have statements and reasons. So our goal, I'm going to put our goal in yellow here. So we want to prove that angle Q is the same as angle S. All right. So right away, what I'm seeing, we have two parallel lines, and I'm going to call RT a transversal because it cuts through both of those parallel lines. And we know, based on what we learned in chapter 3, that our alternate interior angles are congruent. And so what that means is this angle right here is congruent to this angle right here. Okay? So we have two options on our proof. I guess I should return to the proof quickly and say line RQ is parallel to line TS, and line RQ is congruent to line TS. All right, and that's given. Pardon my handwriting. So that's our given information. Our last step is going to be angle Q is congruent to angle S. So we have two options here. Since we have two angles in these in each of these triangles, then, and we have the two angles that are the same, that's another strong caveat. So I should say we really do have we have 4 options, I guess, 4 or 5. So proofs we can take any which way. So I could also say this angle here that I am doing in green. Why did I do 4? So these green angles are also going to be congruent. Same deal, alternate interior angles. So we're trying to prove that S and Q are the same. So we have these two triangles, right? I'm going to erase this because that already confused me. So we have two angles and two sides that are the same. So that side and then this side here in the middle is also the same. So right away, I see that these two triangles are congruent based upon side angle side. So I'm going to say triangle TRQ is congruent to TRQ would be congruent to RTS, to triangle RTS, and that's based on side angle side. So side angle side. Now, if these triangles are congruent, then that means every single piece of these triangles has to be congruent. Now, that being said, we could go through and then we could say, okay, Q and S must be congruent now based upon third angles theorem, but that would take a couple more steps to prove. Me personally, what I would say is okay, so those two triangles are they're congruent, right? So that means Q and S are both in the third slot here. So Q and S are in the third slot. So I'm going to say Q is congruent to S based on C, P, C, T, C. Congruent parts or corresponding parts of congruent triangles are congruent. Our favorite acronym. So I actually don't even need this line because it's four-stepper now. So big picture, we have or it's a three-stepper. We got that proof done easy. So we have our given statements. Then we can say, based on those given statements, oh, you know what? I skipped a step. Oh, terrible Mr. Wright, horrible math teacher. So the step I skipped, I'll put in red in shame. So I forgot to say line RT is congruent to line RT by the reflexive property. I'm writing it all the way out as punishment. Reflexive property. I forgot that step, which is shameful, and I apologize. So I'm going to switch those two steps here. So we use the reflexive property to show that line RT is the same in both triangles. And then we have line RQ and ST are also the same, or line RQ and TS are also the same. And their included angle between them is corresponding and congruent across both triangles, which means the triangles themselves are congruent based on side angle side. And if the triangles are congruent, then each individual corresponding part must be congruent based on corresponding parts to congruent triangles